Ethers are vital compounds in both organic chemistry and medicine, characterized by an oxygen atom bonded to two alkyl groups. Today, we will explore the most common method for creating them, the Williamson Ether Synthesis, and how to optimize its success. The Williamson Ether Synthesis is a classic substitution reaction. By reacting an alkoxide nucleophile with an alkyl halide, we can create a wide variety of symmetrical and asymmetrical ethers through a predictable chemical pathway. To succeed, we need two key players: a strong nucleophile, usually an alkoxide, and an electrophilic substrate, typically a primary alkyl halide. Understanding the relationship between these two components is the secret to controlling the reaction outcome. The reaction follows an SN2 mechanism. The alkoxide oxygen uses its lone pair to attack the carbon atom from the side opposite the leaving group. This single-step process results in the simultaneous formation of the CO bond and the breaking of the CX bond. Because the nucleophile must attack from the backside, the stereochemistry at the reaction center is inverted. If you start with a specific chiral center, the product will have the opposite configuration, a hallmark of the concerted SN2 pathway. However, there is a catch. Alkoxides are not just good nucleophiles, they are also strong bases. If the substrate is crowded, the alkoxide may prefer to steal a proton instead of attacking the carbon, leading to an E2 elimination and unwanted alkene formation. Steric hindrance is the deciding factor. Primary alkyl halides have plenty of space for backside attack, favoring SN2. Tertiary halides are too crowded for the nucleophile to reach the carbon, making E2 elimination the exclusive outcome. When planning a synthesis, always choose the path where the least substituted carbon comes from the alkyl halide. This minimizes steric clash and ensures that substitution wins the race against elimination, maximizing your ether yield. Let's look at a simple example. Reacting ethoxide with ethyl bromide works perfectly. Since the substrate is a primary halide with little steric hindrance, the SN2 reaction proceeds rapidly to form diethyl ether with very high efficiency. To make methyl tert-butyl ether, or MTBE, we have two choices. Option B fails because the tertiary halide only undergoes elimination. Therefore, we must use the methyl halide as the substrate and the bulky tert-butoxide as the nucleophile. Energetically, the SN2 reaction is a one-step concerted process. The transition state represents the highest energy point where the nucleophile and leaving group are both partially bonded to the carbon. Lowering this energy barrier speeds up ether formation. Solvents play a major role. Polar aprotic solvents like DMSO or DMF are preferred because they do not solvate the nucleophile strongly. This leaves the alkoxide anakido and more reactive, significantly increasing the rate of the SN2 attack. The leaving group also matters. Iodide is the best leaving group because it is large and stable once it leaves. Using an alkyl iodide will result in a much faster reaction compared to an alkyl chloride or fluoride. The Williamson synthesis can also happen within a single molecule. If a molecule contains both a hydroxyl group and a halide, treatment with a base can trigger an intramolecular SN2 reaction to form cyclic ethers like tetrahydrofuran. To summarize, successful Williamson ether synthesis requires a strong alkoxide nucleophile, an unhindered primary alkyl halide or methyl halide, and a polar aprotic solvent to ensure SN2 dominates over E2. Remember these key takeaways: always prioritize the least substituted halide as your substrate. This strategy avoids this elimination trap and ensures your synthesis produces the desired ether rather than an unwanted alkene byproduct. Let's test your knowledge. Which of these two pairs would successfully produce an ether? Think about the substitution of the alkyl halide in each case before the answer is revealed. The correct answer is B. Methyl bromide is the ideal substrate for SN2. In pair A, the tertiary halide is too crowded, leading only to elimination. Thank you for watching this lesson on ether synthesis, generated by Vision Solve AI.